Hey everyone, today we're going to talk about the mean and the variance of the sampling distribution of the sample means. In our earlier video, we've talked about the sampling distribution of the sample means, and we can draw information from that sampling distribution with regards to our population. Now we're going to analyze it further using the mean and the variance. Before we tackle the mean and the variance, let's introduce another variable that is necessary for our study here. This sigma here, this refers to the population standard deviation. We've been using this since in our first video in our statistics. So remember that this symbol refers to the population standard deviation. While for the sample standard deviation, we make use of this small letter S. So let's have the mean of the sampling distribution of the sample means. Take note that the mean of the sampling distribution of the sample means is equal to the mean of the population. You can see here, the mean of the population is equal to the mean of the sampling distribution of the sample means. This indicates that as the number of samples increases, the means of the sample gets closer to the population mean. So there are instances where we cannot get all of the possible samples of a population, especially if the population is infinite. So what we can do in order for us to determine the mean of the population is that we continually get the different samples of a particular population, and as we have more samples, the mean of those samples will get closer and closer to the population mean. And the formula for us to get the mean of the sampling distribution of the sample means from the sampling distribution is this one. The mean of the sample means is equal to the summation of the sample times the probability. Take note that this formula is similar with our formula for the mean for the discrete probability distribution. So it basically makes use of the same formula, just with a different notation. But on how we're going to use it, it's just literally the same. Now next is what we have. The next one is the variance. So the variance of the sampling distribution of the sample means there are two ways on how we're going to get the variance. First is if we do not know the value of the variance of the population mean, and second, if we know the variance of the population mean. Population rather, not the mean, just the population. So if we do not know the variance of the population, we can just make use of the sampling distribution of the sample means. So the variance of the sample means is equal to the summation of the mean squared times the probability of the mean minus the population mean squared. So we just make use of the same formula like what we have in our discrete probability distribution. And this is when we do not know the value of the variance. If, however, we know the value of the variance of the population, we can make use of these two formula. This is divided when the population is finite or infinite. When the population is finite, we make use of the variance divided by the sample size times population size minus sample size divided by population size minus 1. This part here is what we call the population correction factor. And for the infinite population, when the variance is unknown, we have here the variance of the sample means is equal to the variance divided by the sample size. So that's how we get the variance. In order for us to get the standard deviation, we just make use of the same formula. It's just that we get the square root. So from the variance, we just get the square root, and there we have it. We have already the standard deviation. We have this particular number here. This is what we call the population correction factor. The population correction factor, we use it when the given sample is more than 5% of the population. So this basically corrects the variance of the sample means if we know the variance of the population. So basically, that's how we go around this one. The standard deviation basically tells us how do these sample means deviate from one another. It is also called the standard error of the mean. This indicates how far a given sample mean is the population mean. So if we have a sample and we took its sample mean, the standard deviation will tell us how far is that sample mean from the actual population mean. So this basically tells us the standard error. So how close or how far can we determine the population mean if we just took one sample? So basically, that's how we go around in the mean and the variance. Let's have an example here. So we have here a sampling distribution of the sample means. We have 7, 7.67, 8.33, 9, 9.67, 10.13, 11 as our sample means, and the probability are as follows. Technically, there is 1/10, 1/10, 1/5, 1/5, 1/5, 1/10, 1/10. But for the sake of computations, let's write this down as decimal, so it's much easier for us. Take note that the sample means is actually x bar. So let's rewrite it as x bar. And the probability is P of x bar. So let's rewrite it as such. X bar. So what we'd like to know is the mean and the mean, variance, and standard deviation of the sampling distribution. So let's start first by having the mean. Remember, the formula for the mean is this one. This is our mean. So let's have first the x bar times P of x bar. So let's insert a column to the right. So we will have here x bar times P of x bar. Here's the x bar here, x bar right there. Then let's compute. Now we are going to compute it the same way with what we've done in our discrete probability distribution in our previous lesson. So 7 times 0.1, that would be 0.7. Wait for a while. Let's convert this into an equation. 7.67 times 0.1 would be 0.767. Let's not round off anything, okay? In this scenario, if we're going to take this, if it's infinite, or even the sample means, let's just stick to 2 decimal place. But for this one, 2 decimal place as well, if there's a very lengthy number. But for this one, if it ends, let's not round it off. But if it's infinite, like 0.3 repeating, let's just settle with 2 decimal place. But if it ends like this one, 0.767, it ends naman, so let's just keep it as it is. So let's have 8.33 times 0.2, that would be 1.666. And 9 times 0.2, that would be 1.8. 9.67 times 0.2, that would be 1.934. 10.33 times 0.1, that would be 1.033. And lastly, 11 times 0.1 would be 1.1. So we have here the x times P of x. And let's get their summation. Let's add them all up. So the summation is, this is equal to 0.7 plus 0.767 plus 1.666 plus 1.8 plus 1.934 plus 1.033 plus 1.1 is equal to 9. Amazing. So this means that the mean of the sampling distribution of the sample means is equal to 9. So that's our sampling distribution of the sample means. Let's now get the standard deviation. Since we do not know let's start first the variance rather. Since we do not know the actual variance of the population, we're going to make use of this formula. So we know the mean, which is 9. So we just have to have the x squared first. So let's have this one. One particular shortcut that we can apply here is we can bypass the x squared right away. Rather, what we can do is this. From here, this one here, we can immediately multiply it with x. Since we have an x here and multiplied another x, it will become x squared. So kind of makes things easier for us in this scenario. X squared, yeah. Let me fix this. X squared, there, x squared. So 0.7, so we're going to get this column and multiply it with this one. It's kind of a shortcut since we have an x here, multiplied with another x, it becomes an x squared. So it actually bypasses the need for us to have the column of x squared. So we have here 0.7 times 7 is equal to 4.9. 4.9. Next one is 7.67 times 0.767. 5.88289. 5.88289. Next we have 8.33 times 1.666. This is 13.87778. 13.87778. Sorry. 13.87778. That's right. 13.87778. Next we have 9 times 1.8, which is equal to 16.2. 16.2. Then next 9.67 times 1.934. 18.70178. 18.70178. Next we have 10.33 times 1.033. That's 10.67089. 10.67089. 67089. And lastly 11 times 1.1, 12.1. So from here we are going to get the sum of the entire data since we are looking for the summation. So their sum would be 4.9 plus 5.88289 plus 13.877778 plus 16.2 plus 18.70178 plus 10.67089 plus 12.1 is equal to 82.33334. Is that right? Let's recheck. Let's recheck, huh? 4.9 plus 5.88289 plus 13.877778 plus 16.2 plus 18.70178 plus 10.67089 plus 12.1. It's 82.33334. That's 82.33334. So that's quite a lengthy number. So that will be used for in this part here. So let's have this equation here. Let's copy this one. So take note that this value is 82.33334, and this is, take note that the sum is the mean is 9, so minus 9 squared, which is equal to 82.33334 minus 81. So let's compute for that. 82.33334 minus 81, that's equal to 1.33334. So this means that variance is 1.3334. How many trees? There's 4 trees rather. So the variance is 1.3334. And in order for us to determine the standard deviation of this number here, let's take this one. We're going to get the square root. So basically, we're going to get the square root of 1.33334. So the square root is, where's the square root here? There. The square root of 1.33334 is 1.1547, or let's just have it as 1.15. So approximately 1.15. So this is our standard deviation, this is our variance, and this is the mean of the sampling distribution of the sample mean. So basically, it tells us that since the mean of the sampling distribution sample means is 9, this tells us that the mean of the population is 9. So if we select a random sample, we can get these numbers here. And our standard error would be around 1.15. So the deviation would be around 1.15. So remember that we can apply what we've learned in our normal curve in analyzing the standard deviation and the mean of the sampling distribution of the sample means. So this is also called our sampling error. So that's it for the mean and variance of the sampling distribution of sample means. Hope you guys learned a lot today. Thank you guys for watching, and see you guys on the next video.